Everyone, welcome to Avenue Code Day 20. This video I'll be live coding my solution in Python so you can see how I approach the problem. Let's get right into it. Day 20, pulse propagation. With your help, the elves managed to find the right parts and fix all the machines. Now they just need to send the command to boot up the machines to get the sand flowing again. The machines are far apart and wired together with long cables. The cables don't connect to the machines directly, but rather to communication modules attached to the machines that perform various initialization tasks and also act as communication relays. Modules communicate using pulses. Each pulse is either high or low pulse. When a module sends a pulse, it sends that type of pulse to each module in its list of destination modules. There's several different types of modules. Flip-flop with a percent are either on or off and are initially off. It does nothing if it receives a high pulse, and if it receives a low pulse, it flips between on and off. If it was off, it turns on and sends a high pulse. If it was on, it turns off and sends a low pulse. Conjunction modules with an ampersand, whatever that thing is, the and sign. Remember the type of recent pulse. Remember the type of most recent pulse received from each of the connected input modules. They initially default to remembering a low pulse for each input. When a pulse is received, the conjunction module first updates its memory for that input. Then, if it remembers high pulses for all inputs, it sends a low pulse, otherwise it sends a high pulse. There's a single broadcast module named broadcaster. When it receives a pulse, it sends the same pulse to all of its destination modules. There's a module with a signal button on it called the button module. When you push the button, a single low pulse is sent to the broadcaster. After pushing the button, you must wait until all pulses have been delivered and fully handled before pushing it again. Never push the button if modules are still processing pulses. Pulses are always processed in the order they are sent. So if a pulse is sent to modules A, B, and C, and then modules A processes its pulse and sends more pulses, the pulses sent to modules B and C would have to be handled first. The module configuration lists each module. The name of the module is preceded by a symbol identifying its type, if any. The name is then followed by an arrow and a list of destination modules. For example, okay, in this module configuration, the broadcaster has 3 destination modules named A, B, and C. Each of these is a flip-flop. Okay, so we hit the button. And it's just going through an example. Okay, to get warmed up, the button also pushed the button 1,000 times. How many pulses got sent as a result, losing the pulses sent by the button itself. And then you just install your module configuration, determine the number of low pulses and high pulses that would be sent after pushing 1,000 times, waiting for all pulses to be fully handled after each push of the button. What do you get if you multiply the total number of low pulses sent by the number of high pulses sent? Cool. Cool. So let's copy this example to start. It seems pretty straightforward. I'm wondering, okay, there are some edge cases, but this is our first example. And And yeah, let's set up the watch script. So I guess first we need to parse all of the lines. And then we'll do 1,000 iterations of yeah. But yeah, okay, first we need to parse the input. Lines. Um, so flip-flop, we need to store, so like what state do we need to store for each module for flip-flop? I guess let's first, we can process the broadcaster line separately. So we are going to parse a type, module type, a name, or I guess we can call this prefix, name, and then maps to. Okay, so it sends the same pulse to all of its destination modules. So can we have multiple destinations here? Okay, we can. Get regular import RE. So first we're looking for either a percent or and. Then we're looking for the name, the space, the arrow, and then just any characters. This could include spaces and shit. Geez. See if that works. Okay, looks like that's working. Maybe let's use this more interesting example as an example. And this again. Yeah, okay, so it looks like that's working. Cool. All right, so thinking about what kind of state we need each one of these types to hold. Yeah, so for the flip-flop, it needs to be, we need to hold position, need position, on or off, and then from each of their connected input modules. And then, yeah, function need type for each input, initially low, off. Okay, cool. I think we can, for the conjunction, maybe we can just use, let's just see what the input looks like, just because I can sort of inform what data structures we use. Okay, it's pretty small, actually. So, yeah. I guess we need like a data structure to hold the state. Um, so modules, dictionary, um, where the name maps to the module data. The name maps to prefix, excuse me, prefix data destination. Um, yeah, destinations. Okay, so modules name is equal to, as we can do, if prefix equals on off, module's name is prefix, and the data will be the position, which is initially off, and then sorry, and then the destinations, which is dest dot split on that. Cool. Yeah, let's models to items. Okay, that looks like it's fine. And then if we have the and prefix, same prefix, same destination. So we're gonna have a dictionary for the data. So data dict stores data dict is name data boolean is false for off, true for on, and then data dict is name maps to false last pulse and last pulse is let's test something out. So we have a dict, it's like 1 true, 2 false, d dot all values, that should be false. And if we said d2 equal to true, all d dot values true. What if we do all true? guess we can just store a string of high or low. No, let's use the Boolean. No, let's just use a string to keep it easy. Okay, so yeah, this may be a little slow, but I don't think that should be a huge problem. Let's just add a to-do though, because I'm not sure if this is the fastest way to store things. Maybe maybe we can just store the same information for each. Um, the prefix is a string, a data, on, off, and then making this more complicated than it needs to be maybe. Let's just finish the problem and then we can go back. Okay. Now let's just run the simulation. Broadcast destination is a list of lines dot split. Whoops. One dot split this. Sorry, this could be line 0. Cool. So range 1000, change to 1 for now. Of the low count, high count. Okay, so this list of 2 fire is equal to, initially set it equal to broadcast destination, and then new 2 fire is equal to delist, and we go from over prefix data destinations in sorry, just name in to fire. And then we can do wall to fire. Prefix data destination is equal to module's name, and then this was set to fire of the new to fire. Cool. So if prefix is on-off thing, flip-flop, and we have conjunction. Okay, first for flip-flop. I guess this should be toFire is going to be a list of tuple of string bool. Where the boolean is if it's high or low. Here, D false for D in broadcast destinations. Oh, can anything be connected up to the broadcaster? No. Oh, so it's not always at the top. Cool. So I guess we need to iterate over all of the lines. And then if line 5 equal to broad, let's see, line 3 is equal to bro. You can set the broadcast destination break. Sorry, continue. GN modules broadcast 2. For name and high and too far. Okay, so the flip flop. Remember, oh yeah, it's initially off. If it receives a low pulse, so if it's high, it does nothing. If high, not high, it flips between on and off. Modules name I guess since we're mutating the data, modules name data is equal to not. modules name data. If data, if it was off, sends a, if it was on, it sends a low pulse. New to fire extend the true for if it was on, it sends a low pulse. Be in dest. Else sending, if it's off, then we're sending a high pulse. And then here is not data. Okay, here instead of a tuple, this can be a list. So the broadcaster sends to A, then A, since it's off, will send to send a high pulse to inv and con. Okay, now we can do the conjunction. Also receives, the module first updates its memory for that input. Okay, so data. So I guess we need to also have the sender. Sender data sender is equal to hi expected 3 got 2 name, the sender needs to be name. Okay. False for low, true for high. And then okay, so we're gonna have to first set up this data dix for the conjunction module. Run 1000 operations. Module data. Okay, so for name prefix data destinations in OD and dest if D if modules D0 is equal to conjunction, modules D1 name is equal to false. Yeah. Your output. I forgot what this output. What the fuck is output? I guess we can do if name in if name if the not in modules continue. And then when we're running the iterations, we can do if high high count 1 else low count plus equals 1, and then this is env, and so what maps to env? Just A. Okay, if data values all and a low pulse from new to fire. And the low pulse send a high pulse. Okay. Here output module's name. If name, I don't know. Print count, low count. Okay, we need to do low count plus equals 1 for the button false. It's a low 1, 2, 3. Okay. Here, this here. 1, 4. Is that right? 1, 1, 2, 3, 4 lows, 4 highs. Correct. What are we printing here? Let's print. Is that right? 2750. Yeah, okay, that's right. Let's copy the whole input of this. Input. I guess we can keep doing that, and then run on the input. Oh, sorry. What are we trying to return? Oh, I just multiply them together. Return high count times. That's interesting and annoying because we get the correct answer part for the example. Rx is Rx input. I guess that's fine. Go back to this first example, I guess. $4,000, $8,000. God damn it. I don't know. Both examples work. What is different about this? Um, guess let's look at this dictionary. There are very few ampersand type deals. This one is triggered by broadcast, interestingly enough. I wonder if that is relevant. Because in the two examples, we don't have the broadcast triggering this conjunction. I don't know. Yeah, this seems like there's some weird logic going on. So on the third time, um, in range 4, something weird with the flip-flops. Mm, the third time, it's going to be here. Broadcast sends a low to A. A sends a high to inv and a high to con. Inv sends a low to B. Con sends a low to output. B sends a low to con. I don't know, guys. I'm just gonna look at like Reddit and see if there are any tips in here. Oops. Just normal, not controversial. Oh, it says part 1. Isn't that hard? Oh my god. I'm just like, it works. Examples. I don't really know what's going on. Like, is it just that I'm missing some logic? I messed up some logic that just isn't covered by the test cases. Um, if not high, I guess, yeah, this is just not data. Obviously, that's not going to change anything. Excuse me. not just clean things up a little bit, but like, uh, uh, do they include broadcast in the dictionary? Um, Memory? Fuck is input map? This looks like it's set up basically the same as mine is. Um, um, I don't know. This is like the same. I just honestly don't know what's going on here. Um, uh, I I'm sort of at a loss for what to do, so I'm just gonna copy this code and see if we get the same thing. Um, 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 this is the more understandable one. Okay. Um, Lines equal um, this is the easy part. I don't. I mean, we're getting the right answers. I truly, yeah, this is just frustrating me. I'm gonna take stop recording, step away, and try and come back to this later. Um, the test keys are passing, the real input isn't, and I'm just not sure why. But yeah, I'm gonna stop for now. Okay, so I'm back. The part one fix was actually quite simple. Um, it was when I'm parsing the broadcast. Here, instead of line, I still had line 0 from when I copied it over. And so that's why I didn't notice the problem on either of the examples because they both have broadcaster, um, sorry, the examples, they both have broadcaster coming first. So stupid, stupid, stupid. But yeah, got that. So part one we were able to solve. And to part two, I was just frustrated, so I was just looking at the answers. But I did still code it up and can explain how it works. So basically, in part two, I noticed there's this RX module that's unattached, and it turns out that that actually matters. Um, and so essentially, we want um, to know when a single low pulse is sent to RX. And to do that, you can see the answer is gigantic. We can't do this brute force. Um, and so basically, if we inspect the input, you can see that Rx is fired by ZH, which is a conjunction node or whatever. Then ZH is fed into by four other nodes, VD, NS, ZH, BH, and DL. And so this would be hard to know without looking at the answer or a visualization of the problem. But each one of these nodes, VD, NS, BH, and DL, has its own separate subgraph. So we can look at this is a visualization someone had on Reddit. Mayoff, thanks for this. So you can see that they have different values, but it's the same, where Rx is fed by a single conjunction. So this will fire a low pulse if and only if each one of these fires a high pulse. So we have for this XT, MK, ZC, and FP, and each one of those is connected to its own distinct subgraph. And so, yeah, we can see it's the same here for, excuse me, yeah, each one of these, XT, MK, ZC, and FP. So essentially, in order for RX to be fired a low pulse, each one of these needs to be high. Um, and yeah, since these are all separate subgraphs, we can calculate the cycle of each one, um, or yeah, the length of the cycle, the period of each one. And since they're much smaller, this is going to be much shorter than the cycle for the whole thing. Then we can find like the least common multiple of each one of the periods to find when Rx is going to be triggered. So to do that, in my code, for part two, we can see that most of it is the same, but then I have this here. We can delete a couple of things. I haven't cleaned this up. But we have, yeah, essentially we have this new dictionary cycle, which I use to track um, the cycle lengths for each one of these um, nodes that feeds into Rx, each one of these unique subgraphs. So here, um, within this to fire, we check if um, each of these, just pretend this is my graph because the structure is similar. Um, for each one of these four, we check if they fire on high. And if so, we update the cycle count. Um, uh, So this gives us something like this, where we get the cycle count for each one of these. Um, it's also notable that these cycle counts, um, so it's going to be aligned. They're all aligned. So it starts all off at 0, hits it for the first time at 3881, then we'll hit it for the next time at 2 times 3881. Again, if these were offset, this would be more complicated, but it's not. So yeah, that's that. And then we can just get the least common multiple of these values and return that to get our solution, which is correct. Yeah, so this one probably not my favorite, which is a sentiment some people on the Reddit were echoing. Well, I was just kind of got frustrated with part one, which wasn't the problem's fault. But yeah, I mean, I don't know how to solve this without looking at the graph. For these last 5 days, I'll try and put in a little bit more time before I look at the answers. But for this problem, I'm glad I did because this would have, I don't know, it would have been frustrating. Um, but yeah, I think that does it for day 20. For these last 5 days, I'll try and upload live codes on the day of. Um, but yeah, if you have any questions or comments, leave in the comment section below. This was kind of a weird one. Um, but yeah, thanks for watching and see you tomorrow for day 21.